because today we'll talk about something that is very near and dear to my heart, which is data visualization. There's a series of books by a man named Tufts. If you ever click on one of his links, you will forever see it in all your social media feeds, because he's aggressively a very aggressive marketer. And you can think of data visualization as sort of your marketing as well, right? It's a very much, I'm conveying my message. And so how to do that and what kind of audience you are, that's what we're going to talk about today. Good morning. Hi, it's Monday. Yeah. Okay, so for example, is this actually switching? Yes, okay. So we talk, we've got everything else down now. We just need to start putting things in actual plots. And so we did a little bit of that last week. But what I want to talk about is how you convey that information. And I think this is one of those really clean, neat ways to illustrate that, because if you see a plot, you sort of think of the position as the main way that information is conveyed, right? Where is it on the plot tells me what the values for that point are. However, I can also do something with the shape. I can do something with the size of the points, for example. I can give them a color. If it's a line, I can make the lines thicker or thinner, or I can give them a different line type. So there are 6 ways on this graph alone to convey information. 6 different ways that you convey information in a simple X and Y plot. Now, my general rule of thumb is you want to make sure that your data visualization actually contains all the data that went into it. So if you have something that is an actual measurement, so a number, you put it on the X and Y position, because with a ruler and enough patience, I can reconstruct your data, right? I can get the points here. I can read off what the values for that point are. However, there's other ways that I can also convey numerical information. I can use it with size, for example. And with enough patience, I might be able to construct a reasonable approximation of your data. Or color. If I'm not too colorblind, I can construct it that way. So it's always important to remember what data you are actually are trying to convey, and the reader, with enough patience, could actually extract from your plot. So if your data is still there, you can still get it out of there, then you're not obfuscating any truths here. Okay, so making a good plot. The most important part is know the audience. And so this is a question a lot of people skip. And they go, where does this plot go? In front of whom does this plot go? Do I make this plot for a general audience? So maybe I'll just skip all the math symbols. Do I make it for, I don't know, a bunch of people's representatives in Frankfurt? I'm trying to convey that this is needed, right? So that's a different audience. I'm trying to show this to preschoolers. I think I'll go with primary colors a lot. These are things like, who am I showing this plot to? Who is this meant for? And so you adapt to the situation as well. So this is medium. If I'm showing a plot here, the plot is usually the size of the screen. You're about, well, maybe up to 20 feet away from it. And all your eyes are great. You'll have good vision, so you can see it. But maybe my audience contains a couple of people my age. And maybe really small font is just mean for older people. And so if I do that on a projection, for example, certain colors really don't come out if they're projected on a screen. They're perfectly fine if they're printed on a paper. So what the situation is sort of situation/medium. Like if I print it on a poster, I've got a couple of posters here in the hallway from students, that's a different medium than it is here. By a general rule of thumb, the simpler the plot, the better. It works on more media. But for example, you could be tweeting no longer tweeting, but whatever social media du jour you want to get your science out. That's the kind of thing where you only have a tiny window, a tiny moment of attention, so you have to get one thing across, like it's the new elevator pitch. If you've heard the term elevator pitch, I think of social media is the micro elevator pitch. Like you can just, that's it. That gets people attention. So that's a different situation, but it can move. You can make moving plots. You can make little movies out of your plots. So that's the kind of thing you would use for that kind of situation, right? So knowing the audience, general audience, or is it a group of your peers where you don't have to explain particular terms, like, you know, everybody knows this, and you go, yeah. Is this the kind of, what kind of situation, what kind of medium, right? Is it a projection? Is it a book? Is it printed? Is it allowed to move? Be precise, include all the information needed. Well, that's a loaded statement. Who decides what the information is that's needed? You do, right? So you need to go, what needs to go in here? This is the kind of thing where, like, what's my message that I'm trying to convey? You have to leave things out. Lying by omission is a thing. Lying by omission in data is definitely a thing. But you have to omit, because if you cram everything in there, you're overloading the viewer. So you have to make editorial choices. If you don't make the editorial choices yourself, consciously, the defaults in the various packages will make these choices for you. So you make the choices, or your defaults will make the choices. Do not mislead. Again, this is one of those things that's at odds. There are many examples. I'm pretty sure there's a whole Reddit on it, where it's like you can talk about misleading plots, right? There's the media, not just social media, but any kind of media, is sort of inundated with dodgy to really dodgy plotting, right? Where, you know, a pie chart where 73% versus 23% and they're the same size, for example. Like, what? But it came by so quickly that you barely, you know, you had to screen grab it in order to see it. So, yeah, that's intentionally mislead, but you can unintentionally mislead. You can even mislead yourself. So mislead is a thing that you need to warn yourself for. Do not use color without thinking, because there are really definitely this says bad color choices. There's your illustration of a bad color choice. A very light color, like yellow or light green, projected on a white background sort of washes out. Cyan is another one. Line strengths that are a tenth of a point, right? It's basically the smallest line strength that are allowed. You don't see them in projection. I've sat through plenty of professional talks where I'm sitting in the back of the audience and going, he's showing an X and Y axes and nothing else. He's talking like there's some kind of data on there, but I can't tell. There's a cyan line and there's a yellow line. Great, I can't see either. So this is a very important thing to remember, that, you know, if you're putting it on a projector, this is the reason that a lot of colloquium speakers will, because it depends from projector to projector, which is the worst, right? So you have your presentation, you try it out on the projector and see if all your plots still come through. Otherwise, you might want to consider a black background. That's where they pop all of a sudden. Do not overload a figure. So basically, be precise but concise. So you have to be editorial about what goes in. And learn a couple/one package is usually good enough, but maybe a second. Matplotlib has just about everything you need. However, there are others. Like I've used Seaborn a little bit because it has a couple of convenience functions that are really nice. But yeah, there's a couple of packages. There's multiple packages in Python. There's always a couple of rival packages, and there's different ways to do the same plot, basically. Okay, so adapting to the audience. I think this is one of the best plots I've seen. You go like, it's a histogram. But leading causes of cancer death. So you have the number here, they're on the same scale, and we've put everything easy to read because, so why did we swap? If you put a histogram, you usually put the histogram, like the causes you would put on the x-axis. But then you would spend the entire time reading like this. So one of the editorial choices was, well, if we have to read these things, I'm going to put them like this because the numbers are relative. That's the most important thing I want to do. So I already made a balance of what was the most important thing to get to you and the least important thing to get to you. The most important thing is which one. Relative is something that I can read horizontally as well. Women, men, I've color-coded it as well, just to make sure that you know that these are different. I have new cases, and then the red bar is fatalities. I apologize. We all get, we all encounter this either in our family or ourselves at some point. It's almost inevitable. So it's actually good to have this kind of information where you see things like, well, I've got prostate cancer here, for example, and there's like lots of cases, but it's not terribly lethal. We figured out how to treat that. And there are ones that are lung cancer. It's like, yeah, that's a pretty lethal disease. Who am I aiming this for? Is this a general audience? Or is this, for example, the NIH governing board? So the National Institute of Health. All right, it's like, okay, if I put money here, where can I get where do I save the most lives per dollar? It's like, well, if I put it in here, yes. If breast cancer, actually, that's down by a lot, right? But even then, if I get a few percent more, that's almost as good as the other ones. And then there's a couple that are really rare, and I'm like, well, maybe they get a little less priority because there's not that many people. Like it's a hard kind of decision that you have to make here, but this is how you convey and how you can easily, immediately see where to go. So editorializing also leads the audience. You are leading, but hopefully not misleading the audience. This is the editorial choices you have to make. Okay, so adapting to the situation, adapting to the medium. For example, I have a scientific paper here where I'm showing the 250 trajectories of a dual particle system. So it's like, here's the X position, here's the Y position, and where do they end up? Do they actually stay bound, or do they, get removed, get out of each other's way? So this is fine. I'm showing my entire in-body, like this is all my simulations, like this is all of them combined. If I put this on a poster, I've basically like, oh, there's a red onion and 2 blue layers or something like that. It's just overloaded. There's way too many of these. This stuff is still, exposition is small. Font is too small. Like usually my comment will be the font is too small. There's only a few cases when you really can't stick your title on the poster anymore when your font is getting too big. There is almost no upper limit to the font size that you can use. If it fits underneath here, it's fine. So make the font as big as you dare. But if I go to a poster or like a smaller, suppose this is like a social media post. This doesn't convey it. Here I can just give a couple of examples and it's clear enough, right? So actually subtract it. So a lot of data visualization is subtraction. Like, what do I need? What's the minimal stuff I need to convey it? But also, I've made the font size larger, 0 to 1. I don't have to actually show all that stuff. This is the minimal version of this guy. But I did blow up that starting position because otherwise it wasn't clear. So I've highlighted a few things and removed the rest. Very much editorialized the original data. Yeah? For example, this is the absolute, XKCD is always like the minimalistic optimal, where you start with like far and near, human proximity to cat, intelligence drops, inane statements goes up, right? It's like, you're a kitty, and not only that, the reason that I love this part is that I'm actually illustrating the x-axis with a little cartoon. Far away from cat, medium distance to cat, closest proximity to cat. So this is actually a good thing. Like I like this because I can immediately go into, hey, if you have a scientific poster, you're going to a scientific meeting, the very first way that you convey your science is typically a poster. This is a good scientific poster because it does everything with a minimum number of actual words. Words take time for people to read. People Read the fastest, talk the slowest. So if you can get it across by reading, that's already faster. But if you can get it across by a cartoon, that's even faster than that. Pictures are the fastest, then reading, then actually you talking to them. I'm just talking about how fast you can get the information in that person. And I can tell you from experience that if you're a student standing next to a poster and professors that you want to go to grad school or somebody you want to talk to, or Lockheed Martin representatives that you wanted to chat to about possible jobs, they're on their way to the coffee. You're between them and their caffeine. So they're sort of trudging along going, oh, yeah, okay. So you have that to get it across. So you say, title, here it is, oh, proximity to cat. Like I can actually use a little visualization like that. There's usually a little cartoonesque visualization. You can either on the x-axis or the y-axis, or for instance, the label and the inanity of statements, for example, you can put the label as a picture. That works, for example. That way, you have everything you need. You don't need to read any of the words because people don't usually spend enough time with a poster. They've been standing and running around all day. They kind of want to sit down with their coffee so they can see immediately what you did. So you made some editorial choices and you subtracted a bunch of the information, so just the essence comes across. Okay. So why do we make visualizations, right? We already did a couple, and we did them to essentially check. That's the first, that's the one that's not on here, but that's usually we make a first plot to go, is this working? Is my model actually over the points or nowhere near them? You can't tell that from a table, or at least, please, when you ever do a presentation, never show a table. Tables are useless. Nobody's going to memorize, not even people with photographic memory are going to memorize a table. They're not plotting this in their head. You're going to plot it up. So you have your table, you plot it up, and you go like, look, a line goes through points. That's 90% of scientific talks. Points are the things we measured, line was the model, look, they agree. So it's a first check that you do. You can help with your argument. It helps your argument if you have a visualization that's clear. Here's the data that other people took. Here's my model. It goes, shoom, goes right through. You summarize a lot of data. Instead of having to say, here's a table with 1 million, and to show you a cloud of points. You can discover new relationships. This is, I think, a very important one. You plot x against y because you're like, wait, are those two related? Is the amount of effect that I'm seeing related to the lab's temperature? Let's check that. Oh, I'll plot temperature versus the thing I'm measuring. Relate different pieces of information, especially disjointed ones. So a lot of people that do research with me, for example, get two tables. They match up the two tables. Everything goes for the same thing, but then we look if there's a new relation between those two, between one column from catalog A and a column from catalog B. Hey, are these two things related? You try to avoid things like bigger things are bigger. You're like, okay, fine. Or more massive things are bigger. And you're like, yeah, I didn't discover anything. Hi, have a seat. And you can start developing some intuition. So if with most science, we started by butterfly collecting, right? We just looked at different kinds. Like there's white butterflies, there's black butterflies, there's these, you just made groupings and hope that you saw some kind of relationship. You can sort of do the same with data. You plot every possible column against every other possible column and see if something interesting pops out. That's sort of the brute force, I have no idea what I'm doing, but I need to develop some intuition. So I'm just going to plot everything against everything. If all else fails, you can always do that. We do that a lot. It's called exploratory data analysis, which is essentially saying, I have all these columns. I don't know what's driving what. Let's look at correlations so I can look at the plots. So good visualization, the definitions are pretty personal. They are very much dependent on situation and you. You can be, for example, absolutely fine with the color combination, I don't know, orange and yellow. While other people go, oh, no, that's just not working for me, right? Or bright green and bright yellow is a good example. Like I've had people who've done this in an Excel sheet where they made one line green and one line yellow. And that's good to sort of separate them out, but at some point, everything starts to swirl together for me. My definition of a good visualization is that it shows the data, it minimizes the clutter, and your points survive shoddy photocopying. So suppose you have your plot, and I fax it to you. If some of you have maybe heard of the technology faxing, it was ancient when I was in your but people seem to not be able to let that one go. So I have had my papers faxed to me with comments on it. So it's like if I could still read what was going on after it had gone through the fuzzying up of a fax, I'm pretty sure that my plot conveys the information. If it's a color plot and I suddenly make a black and white photocopy of it, I would like that information to survive, right? I would be able to see what happens to it. That means that if somebody, shrinks your plot until puts it in the corner of their talk, it's still clear what's happening. That's really solid visualization. And ideally, a very patient person, I'm sort of thinking like a really bloody-minded monk who goes like, no, I have nothing else to do. I am getting these million points out of this plot. They could potentially do that. It's the information survives in your plot, right? There are some, like I said, there are some actual awful visualizations. Let's look at this one. This is one of my favorite awful visualizations because apparently the average female height, in Latvia, there's these giantesses that could possibly stomp on anybody in India. What's wrong with this visualization, apart from the fact that everything's pink? Yes?
Well, for one, they didn't just use like lines, they used people, and then they also scaled them up based on like and it's also like because it's starting from like 5 feet, like yeah. It's not small.
My feet, their feet, anybody's feet aren't at 4'9". That's not where you start. So this difference is, what is it? About a hand length, right?
Probably a bit more.
Yeah. So if this started at 0, basically everybody was almost the same height, and you would get something like this, right? You can show, you can do the whole person. The whole, showing the person immediately conveys if you're talking about heights of people. That's not so bad. It's the fact that we put the 0 point at 4'9". This Indian woman isn't 1 inch tall. The average Indian woman won't get stomped on by anybody from Australia. It's like this is a relatively small difference. And it's the average height, right? It also doesn't convey quite well what the range of values is. And pink is a little overused, I would say, for these kind of plots. Wolf sightings. This is one of those favorite things. Like, what happens if I stick all my points on a map? Usually that's sort of like a knee-jerk reaction. If anybody gets data, you go like, all right, well, let's see where this all happened. And that's all well and good, but do you think wolves live up here in Canada? Probably. What, no wolves in Eastern Europe, or none in South America? So this is clearly not complete data, right? It does tell you something. However, everything is so bunched together, it's really hard to tell how many wolf sightings I'm talking about. Like, how many wolf sightings are there in California? I mean, I can tell that there's more than one. It's cute that you use a little wolf for that, but it doesn't work on this scale. So you can junk up your data, you can junk up your chart very, very quickly. So this is an excellent example. This is the kind of thing that if you start with one series and you have a blue line, you go like, yeah, this is great. And sort of this is all the defaults, right? There's a mesh by default. We're showing all the numbers by default. And I'm just adding a couple of more series just to see if they all agree, right? So this is very much a thing like a boiling pot kind of situation where it's like, one's fine, I'll just add another, I'll just add another, I'll just add another. So what junked up on this side? Let's have a look. I can't read the x-axis for the life of me because all the points are basically meshed together. I can't even tell if this is, it's 0 over here, I think, but I have no idea what the end point is because it's basically all sort of flow together. Defaults will do that to you. Eventually, they'll do that. I can read the y-axis, although nothing's labeled, so, no idea what that is. Millijanskis, Kelvin, number of gerbils cited, who knows? So the thing is that I have 7 time series, and I'm trying to actually, if I want to follow any of these lines, one, I better not be colorblind. Second thing is that some of these don't stand out as clearly to the background as it is, and I mean, let's find the red one. Like, okay, it goes up here, goes back down here, gets jumbled here, goes up. With great effort, I can follow one of these things if I completely ignore everything else. But that was not the point, right? I wanted to intercompare. So it might be better just to split these things up into their own little graph. So here, it's each of one of them is a series, and I wanted to see if they agree, right? So I put everything else as a gray. If you dim it a little bit, if you make it a little more transparent, it goes towards the background. Our eyes work this way. Things that are bold go front. Things that are not completely transparent, so alpha is the way that you do transparency, sort of fade into the background. You can still see them, but you sort of compare it to whatever's bold. So I have a bold line here. I can intercompare like this. I can intercompare to whatever is in the background. I can see the numbers here now, and if it's not that important, I'm just interested in the minimum and maximum values, I can put it like that. But I made a couple of different choices here. Yeah? Okay. Another thing is that I'm just completely relying on color to separate them out. If I don't want to do that, I can do things like line style or line thickness or line transparency in order to sort of separate things in sort of our perception depth. Okay. Here's an example of odd data. I'm doing it. I'm showing you a table. So I've shown you the data. Look how odd this data is. Right? I've got an X and Y, an X and Y, so 4 sets of data. The mean is 9. The mean for Y is 7.5 for all 4 of them. The variance is 11. The variance for Y is 4.12. The correlation coefficient is 0.816. So are these the same data? The best fit line is Y is 3 plus half an X. Are these all the same data? Are these samples that are indistinguishable from each other? I've given you the mean, I've given you the variance. I've told you that X and Y are closely correlated with the same level of correlation function. We'll get back to correlation coefficients, by the way. So these must be like basically points out of the same time series, yeah? So this is what we were able to do so far. We've got X and Y positions. We can tell our stats, and our stats are telling us these are identical. So they must be very similar. This is why every professor says, make sure you plot your data as well, because this is the data. If I fit a line through this, it's a straight line. I can fit the straight line through all 3 of them. But this is some scatter around this relationship. This isn't a linear relationship at all. This one is a linear relationship, but with one outlier. And this one has no relationship, but has one outlier, which could be, this case and this case. I would start getting really suspicious. What happened to that point, right? Especially here. It's like there is no correlation between these two. There's just one outlier. So you're being pulled in one direction by one outlier. The bottom line is always plot the data. Because if you go like, oh, yes, there's a correlation coefficient, I'm done, I'm out, here it is, scientific result. People will want to see the plot. Okay, for example, this is an X and Y plot of a dinosaur, and it has the same variance along X and Y. As is this, as is this, as this, same variance, different distribution point. It has a particular, it's unstructured, right? Variance only holds if it's a Gaussian distribution. So if you're doing histograms, or if you're trying to plot data on, one axis, it's important to remember that the box plot is one way to show, this is 1 sigma, this is 3 sigma. That works great if the distribution is Gaussian. These distributions are Gaussian, so if I show the same sort of but binned along the y-axis, you have the violin plot. Now, what happens if I start messing with that? The variance stays the same. The box plots stay the same. So if there's underlying structure, I threw it away with the box plot. Okay? So if I do a histogram like here, it actually shows no, there is all kinds of underlying structure. Here, it's no, here's the standard deviation. I just calculated the standard deviation. There it is. The underlying assumption is that it's Gaussian. So if you show error bars, people are going to assume, because you're showing them that the underlying distribution is Gaussian. So if the underlying uncertainty is Gaussian, that's what you should plot. If it's not, you should plot something like this. Okay. So a graphical display should typically show the actual data it's made of, induce the viewer to think about what's actually being shown, avoid distorting what the data has to say, present as many numbers in a small space as practical. This is where it's you have to draw back a little bit. Make a large data set coherent and immediately ingestible. Encourage the eye to compare different pieces of data. Reveal the data to several levels of detail. Be relevant. Show the units. Always show the units. Always label everything. So that's tough to visual display of quantitative information. It's a very good series of books. For example, color choice. Now, one of my favorite things in the world is maps. This is sort of the first where we start conveying a ton of information in just a single 2D visualization. So this is Hokkaido, that's mainland Japan. Here is Vladivostok, so that's Russia. And this is the Sea of Japan. Here's a choice for colors that you kind of go, what was the idea here? You can have a different color gradient where 0, for example, is white, which is the sea level. There's a natural 0 here, which is sea level. And then so anything that's brown, one side of that is dry land, and anything below that is blue is sea. So you can, for example, see that the Mariana Trench is really, really deep. But if you do this is sort of a random choice. Why is this red? Right? So those are essentially really, that's the shallow parts, and this feels like a really deep part, but it's actually just one step in scale deeper. So it's there's actually not that much deeper than the rest. So having a natural step size, an intuitive step size helps. So there's a tendency of physicists and astronomers to choose a small set of color schemes or just stick with the default in their images and plots. Sometimes this leads to misrepresentation. In fact, a lot of the time. So here, for example, we have in sort of a 3D contour shape 4 different things. And here we just stuck to Viridis, which is our usual color scheme. If you go to Python or many other plotting programs, they sort of stick with this as your color scheme if you don't specify any. So I can see there's something yellow here, and the rest of the whole brain here is greenish. Same thing here with this jet engine. Same thing with Maryland here. And down here is all of Mars that I've sort of plotted in same scheme. Now, Chesapeake Bay, note the artificial structure at higher altitude when there's actually quite gradual. It feels like there's a mountain here. It's not, but it's a different color, so it's becomes more prominent. A slice of an MRI scan, washing out the detail in all this part here because there's a high value right here at the bone. So that's it. You just highlighted the bone in the skull and nothing in the brain. And well, I was actually after the brain, please and thank you. So here's turbulence flow in a jet engine. Well, I actually want to see the small scales here. And Earth magnetic field for Cartesian projection. So where's my note the smooth structure, so I actually want to see what the larger structure is. So you can pick other things. For example, we have a natural 0, that being, this is dry, that's wet. You should always put that at 0. So you can have a divergence from there. So you're like, oh, actually, this is all pretty flat land, with lots of little inlets, which, I couldn't quite see here, with lots of little water inlets. So it's lots of water, dry and wetland. High frequency information, best with a variation of luminance. Actually, color is terrible here. You just want to use grayscale. Grayscale is good. Our eyes are great for detail because it has all the rods, right? Remember that you can still see a lot of detail at night because you sort of ditched the color part. And it's like you can see lots of detail. So grayscale is actually your friend here. And so you can, if you have an instance where you want to see the shock waves or you want to see the fine detail, grayscale is actually better. And then low frequency information, so large scale information, a color variation saturation is good, it's fine. Like you can actually do different colors. One key lesson, try some different color maps to actually get it across. Your data will be most clearly served with a different color map. Okay, three kinds of color maps. You've got sequential, diverging, and qualitative. Yes? I mean, if you're having a little bit of a deja vu and go like, I feel like I had this when we did finger painting. Yes, a little bit, right? It's color theory as of what you got in art school, in art class. But this is important, right? It's the kind of information I want to convey. Do I just want to make sure that you can tell A from B apart? I can give everything a random color as long as they are, different enough to our eyes. The color in itself doesn't mean anything as other than this isn't that. So maps are a great example. Like that's Serbia, that's Kosovo, right? So you make little red, one red, one blue. So they're neatly, clearly separate. Divergent is the kind of thing that you use for temperature. You have a natural 0 Fahrenheit, 0 Celsius. And anything lower than that is blue, and anything higher than that is red. You've seen people do this on weather. You can do that with maps, like we just showed that, right? Like on one color means above sea level, this means below sea level. So divergent is useful for things that have a natural 0, and then it's interesting to actually say when it diverges which way. So you can easily group things one way, like these are all cold, these are all hot. These are all lower than sea level, that's all higher than sea level. But with sequential, you can actually get the data back, right? So things like, it's green, so let's say amount of vegetation. So as it gets more and more, it actually gets lighter, so that's counterintuitive. So let's say amount of grazing by cattle. That's one of those things that you want to plot on a map. So very little grazing, lots of grazing. And so it can actually figure out what value it roughly is. Somewhere in those 10 steps, I can grab that. And it's like, okay, so 40% grazing lies about here. So I can actually get the data back from the color scheme. Yes? Okay. Color choice is really important because you can lose your audience, 10% of your audience instantly by using the wrong two colors to do. Can everybody read these numbers? Yes? Can everybody read the numbers below? Have you all had this test? Surely, right? So better use safe color palette for people that basically see this as black and white. If you use red lettering on a blue background, I will find you. This is the quickest way to give me a migraine. It is absolutely horrible, and never ever do this. All right, so I needed to get a laugh out of you all in the morning. But we have these different color maps in Matplotlib. And I just Google Matplotlib color maps. Here you go. But as you can see, not all of them are gradients. Not all of them are divergent. So these are sort of like, I use this kind of thing if I just want A and B to be different. But it repeats. So it just says, separate things out. There are ones that are sequential, and so you can sort of go like, well, my favorite color is blue purple, so I can go with purple to red, for example, but or purple blue green, so I can actually get a gradient like that going. Or you can just do greens, like, you know what, I just like green, or blues, and that gives me from light blue to dark blue. So it's both. Those work well for because they survive photocopying, right? It goes from light to dark, so I can still see that after I turn the whole thing black and white. Yeah? And you put this color map next to it with the values that agree to that. So the color choice, 10% of the population might miss it. In Seaborn, there's a couple of palettes, and there's a page here. But effectively, for me, it's always, well, what happens if I either turn it in Photoshop to black and white, or I literally copy the thing? If I can still see it, great. That means my colorblind friends can still see it. 10% of your audience to lose on something like that is not healthy. If you have 30 people in your audience and you agree suddenly, that's a big part of your audience that now is going to start scrolling their phone. So, okay, so the color wheel. Yeah, we've had the color wheel in art class, yeah? So you want to do things that are complementary. So one of the reasons, for example, that certain flowers have, for example, yellow and orange, or we like certain compositions or certain artistic compositions, is because they're complementary. They're on either side of the wheel. So if I use these two, they separate out. So sample A, sample B, they're suddenly like very separate. You go like, yeah, you told me not to use cyan. Oh, you can use cyan. That's fine. But I would make sure that I put a line around, make sure that it has a border so I can actually see the point. And it's like, oh, those are cyan, those are red. They pop. And especially if they're on top of each other, they pop out. They sort of separate out for us. You can do triadic, like yellow, blue, and green, and they separate out very, very clearly. If all else fails, go back to primary colors, right? If you go like, wow, this whole thing looks like it came out of Sesame Street. Great, wonderful. It's easy to follow. There's a reason Sesame Street uses it. It's much better thought out than you think as a 4-year-old. So you can even go red, purple, cyan, and yellow, and those three will separate out very well. Now you can go monochromatic, but then your visual clue is that they're all the same, right? They are the same population, just different gradations of it. Your eye will refuse to go, these are completely different from these. Like, no, they're the same color. So subconsciously you go like, well, those are the same, just different versions. So if you want to show something that are different versions or different gradations, that's fine. But don't say like, deep orange and light orange are completely different. Don't do that. You can do analogous, like, for example, with like just grades of blue, right? So it's like, instead of, this is just more intense of the same color, this is literally going from light blue to dark blue. Same thing goes, right? So same thing goes for that. Like, you have to say, like, these are sort of the same family of points. Okay. Distributions, back to distributions. So we just showed that, right? It's like, okay, well, how do I solve that? The thing is, we've made histograms, and you didn't make any choices. With a histogram, you make a choice. How big is the bin, and how many bins do you want? And if you don't choose that, Matplotlib will just make a guess for you. You go like, you want 10, well, it doesn't. A baker's dozen bins. That's about right. It does an okay job of that, but this is literally the data gets obfuscated here. If I say like, okay, how many like values in the middle here, I can tell you how many values with a little bit on either side. Like, that part has become unclear. I can't actually retrieve the data here. If I do that, I've lost a significant digit by amount how wide that bin is. So there is a term calling binning the hell out of the data, because I couldn't see the effect first. I just bin the hell out of the data and see if I could see it then. But that means I'm removing information. Yes, I'm sacrificing information by smoothing it effectively. So that's sort of what you do here as well. Here, this is not a single individual point. This is smoothed. So I've actually lost a little bit more. Here, the data is still there. See the rug on the bottom here? See all the little dots? That's where my data is living. And that has resulted in this smooth histogram. Or I can, put these at the bottom here. Now, most people don't do that because they find that a bit, visually cluttered. And so your default matplotlib histogram doesn't have it there. But this one doesn't lose the data. It shows the distribution, smooth a little bit, sure, but it shows the distribution, the probability of each point happening, for example. But here you can actually get the data back. And so you can do a combination of the two. It's like, hey, here's the smooth version. This is the actual, bin histogram. You can even put those at the bottom. So there's different ways to show one-dimensional distribution, a series of points. These are the measurements that I've taken. But for example, I'm really interested if the peak is actually where I expect it to be. Then this is right. It tells me where the center point is on all. That's okay. I mean, what am I trying to get out of it, though? But the nice thing is here that I can keep my data if I don't show it anywhere else. So the violin plot actually does that a little bit, right? You can see the standard deviation in here because you're like, okay, this is the standard deviation. So if you assume the whole thing was Gaussian, this is what it would look like. But it's not. All these things have tails. And a lot of distributions will end up having a minority of outlier points. And it's so easy to go like those are not important. But often they tell you something. There's a minority report happening here in some of these. Like, look, this is clearly not a Gaussian. This is a couple of distributions on top of each other. So this is why I use these violin plots, because they sort of double up the histogram and show you like, it's fat over here. There's like a bunch happening here. And is my assumption that it's Gaussian okay? And the answer is like, well, in all of these cases, not so much. Something more complicated is happening. Subpopulations might be happening. So if I do this with like, okay, well, I just, just put them in bins, this is the histograms that you typically get. Like PLT hist spits this out immediately. It's the kind of thing that you want to look at immediately. But there's other ways to do it. You can do two-dimensional histograms, for example. So how do I do that, right? Do I bin here and here? So here's one histogram, there's another. That's great. But I can also see in these hex plots, so this is called a hex plot, actually the density of where points are. So I can actually see that there's two smaller subgroups there. So I can actually find subpopulations that I wouldn't see in the one-dimensional histograms. I can see a correlation here, and I can see subpopulations. So I actually get a little more structure out of a two-dimensional plot rather than the two one-dimensional histograms. Going a little too fast? Or this is the kind of thing like, so this is the kind of thing you do in order to get correlations, get some visualizations, go like, oh, here's a subpopulation I need to go look at. You can also do that while it's smooth, so you get a contour map, very much like an ISO plot. So isothermal you've got, and then you've got ISO, I keep forgetting what the term is. I had it back in geography days, but it's the same, it's ISO altitude, so it's the same height, right? So you could have, for example, this is a lake and that's a mountain. And so that's how you contour map. So you can use the contours to sort of show how much are contained. Why would you do this, by the way? You would do this because if I show the points, if I just plot 1,000,000 points, this is a solid black or a solid dark green, whatever you've used, but this is a solid blob of points. I can't see structure in there. If you bin it a little bit, or if you use contours, you can see structure. But as soon as I go outside here, I lose individual points, so I don't see any out. Again, I made a choice. I had to make a choice because I want to see structure on the inside, but I don't have contour, I don't have information on the outskirts, right? So often people end up combining these with individual points. Like, so basically at some point they go, okay, it's now just one blob of points. I don't see anything anymore. I don't know if, it's completely black with points. Okay, contours it is. And then outside I have individual points. So that's what this is, right? So I do, if I have multi-dimensional data, I do this, I plot every x against every y, and I do the histograms on the diagonal. So contour plot, and then, so this is GR, and this is GR, so that's this one flipped. And this one is this one, but here it's in contours and here it's in individual points. So you can see a bit of both. And then for each individual of these different parameters, which I will point out, small, the font is too small. I can't read it from here, so you have no hope of reading this. But you do the histograms on the diagonal. The neat thing for this is like, this is the kind of thing that Seaborn spits out really fast. The nice thing about this is that you can give it an enormous data file and go, is anything related to anything else? Or is everything, neatly linear related, or is there something odd? Is the distribution Gaussian? Like, you can just visually check that immediately. So it's sort of, this is a exploratory data analysis. Like, you just throw this up and go, okay, here's some interesting thing. Let's go look at that in more detail. If you have lots of columns, this is the way to go. I have to always show in more XKCDs, this is the worst kind of plot and the best kind of plot, right? If this is the size of the wall of the room, if this is an enormous poster, you could go up and go like, oh, look at the, these are all the different characters of the movie. This is the, 24 hours that the actual Lord of the Rings takes. And you can sort of see which character goes with what character. Same thing with Star Wars, the original trilogy, Jurassic Park, 12 Angry Men, and Primer. And I have no idea. That's sort of like a movie like Inception, where it's like you have no idea what's happening or what character is who. So it's just one.
Well, like, yeah, time travel.
Yeah. So, but this is kind of neat to show which character interacts with which character. And so, but individual cases, very hard to follow. So if this is the size of, that entire wall, it's fun to do. But it's too small and too fiddly to do work with. Also, the color coding sort of says, like, this is an elf, this is a, yes, I'm aware this is deeply nerdy. Point is that you sort of have a legend of, like, who is doing what and where. And so you can sort of summarize a plot that way. Yes?
Now I'm questioning if they, like, sat down and, like, made that by watching the movies themselves, or if they cribbed that from somewhere else. Because it seems like a lot of effort to put in for, like, a weekly comic to make
That's what XKCD does. Yes, he did. Yes, he did.
Man.
Yeah, it's special. So you can definitely, sort of step through it and basically figure out who is where. I'm pretty sure this is a plot, though. So minimalism is like, this is too much information. It basically tells you what kind of character. This is nice minimum amount of information, right? I do actually plot the X and Y, what's on there, and I've made like one thing, and like, here is an inflection point that I want you to draw your attention to. So that's what I wanted to point out. Minimalism is good, so subtract once you have your first. Remove what you don't think you need, and then make everything else a bigger font until, the biggest font you dare to get away with. So that's it. We will work on the first X and Y plots this week. We started last Friday, and we have another one, assignment 6, which is sort of like, how much information can I cram in my X and Y plot without, sort of overdoing it. And so those are the two things that I want to talk about. We'll talk about data visualization some more next week, and I want to start to talk to you all about your midterm presentations. Yes? Okay. See you Wednesday. Sorry for going over 5 minutes.